Okay, I guess maybe we can start. So last time we started looking at the Poisson formula in the classical setting, and then we said several times that one of the goals, at least of this part of the course, is to introduce the Poisson first number boundary, which is a generalization of that Poisson representation formula to an arbitrary group action. So let's briefly recall what was the classical setting. So in the classical setting, we have the following formula for a disk. So in the disk, we had H infinity of the disk, which were bounded harmonic functions. Harmonic in the classical sense, so the Laplacian vanishes. And then we have this other space, which is L infinity of the boundary with respect to the Lebesgue measure, which are clearly just bounded functions. Let's say essentially bounded. And then the classical representation formula exactly says the following: that given a function f on the boundary, a measurable, bounded, and measurable, we can define the harmonic extension inside. So we have u of r e to the I theta to be the integral 1 over 2 pi, the integral from minus pi to pi of f of e to the I t. And then there is this Poisson kernel that we described and analyzed last time. So this is indeed. And so once we have that, then u is harmonic and bounded. And then last time I did this calculation, and now it's also on the next version of the notes that showed how indeed this formula that seems complicated indeed can be thought of as a integral with respect to measures that come from the group action of SL2R on the boundary. So the group here is, once again, is G SL2R, which is, or let's say PSL2R, which is the isometry group of D. And of course, this also acts by homeomorphisms on the boundary. And so in fact, what you can say is you can define the formula in an easier way, which was the following: that given a point inside, you pick GA in this group of isometries, so that GA of A is the origin, 0, and then we can represent the value u at A just in the following way. It's an integral over the boundary of what? Well, you take the function f, which is a function defined on the boundary, and we push it forward by this map. So, for instance, we can we can write the integral like this. So is f of GA psi d lambda. So lambda is the Lebesgue measure of psi, or which is the same because just of the push forward formula, this would be also f of psi d GA star. So this is the push forward of the Lebesgue measure when you integrate it. So this is this intriguing computation that we did last time, and now we can realize that this context that we have here is very general, because basically we can do the same thing for any group action that you have, basically. And that gives rise to the notion of a Poisson transform. So let me give a definition of that. So in general, we have what's known as Poisson transform, which is we start with a group with a measure on it, measured group, and then we have a boundary, so candidate boundary. So what is the first thing that boundary needs to have is that, well, first of all, it has to have an action of group on it. So, and then it has to have a measure, and the measure is stationary. So the definition is like this. So we call it a G-mu space is a is a measure space B nu where G acts on B by measurable isomorphisms. So measurable maps with measurable inverses, even though most often it will act by homomorphisms, but I don't think it's needed at this level. And nu is mu stationary, meaning that mu star nu is nu. So this is the first thing that is required. It's not the only thing. But once we have this, we can already do the first step, which is to construct the map. One map between harmonic functions and bounded functions in one direction. And so this is called the Poisson transform. So we say the Poisson transform is the following: is a map phi between L infinity of B nu and H infinity of G mu. Remember that this one on the right hand side is the space of bounded harmonic functions on G, and it's defined like this. So you pick a function f on the which is bounded on the boundary, so it's an L infinity, and then we want to know how it acts on G. G is an element on the group, so this is in L infinity of the boundary, and this is in G. And we do exactly what we did before. So basically, we take the function f, take the measure nu, we push forward the measure nu, and we take the integral. We pair it with f, and we integrate over b. So this is an extremely general process. And what it turns out is that this process gives rise to a harmonic function, which is not completely trivial, but it's It's a fairly simple calculation. So the lemma is the following, then that indeed phi of f is mu harmonic for any f and so we have to prove that. Okay, so let's look at the proof. The proof is fairly straightforward. It's just a calculation. So what do we need to check? Well, we need to check that if you take phi of f of gh and we integrate with respect to h, yeah, we'll have to question whether is this the same as phi of f of g. And so now we literally just write the definition. So what is this? Well, this is the integral over g and phi f of gh. You have it written up there. So it's another integral. It's the integral over b of f gh psi d nu psi, and then we still integrate in d nu h. This is just a definition of phi. And then, fortunately, there's really not too much to say because this is, by definition of the convolution, this is the integral over p of f of, I don't know, let's call it eta. Let's say that eta is gh psi, by we do this sort of change a variable, and this is d mu star nu of eta. This is definition of what convolution means. And then we know that mu star nu equals nu by the fact that this measure is stationary. So this is the integral of f of eta d nu eta of b, right? And this one is, by definition, is phi of f of, wait, sorry, sorry, there's a g, yeah, sorry, I don't need to do gh, just h, yes. Sorry, the g should still be there, yeah, okay. Yeah, so we do the change of coordinate eta is h times psi, not gh. Anyways, this is just the computation, and once we have this, we know that this map is harmonic. So of course the problem here, the question that one can ask at this point is that is phi a bijection? So we know that phi goes from L infinity to H infinity, and of course the easiest thing to do would be to say, okay, B is just a point. Then if B is a point, every measure on a point is invariant. So G star nu equals nu, and so basically there's no dependence on G anymore, and so you get a constant. Right? So this is obviously first remark is that if B is just a point, then yeah, the image of phi is just constants. And of course, this may not be the only thing if there are other harmonic functions. So if more harmonic functions This is not. But basically, the definition of Poisson boundary that we will see soon is built so that precisely you get that this transformation phi, this transform, is an isomorphism. Any questions so far? Okay, so what else? Now let's now we need another step. So we don't need just the notion of G space. So here we introduce this notion of G space, which is useful, but in fact we need a further notion of boundary to make this really a theory of boundaries for Rhino-Walks. And so we need the second notion, which is a notion of new boundaries. So again, this is another definition. So new boundary is a bit stronger than just G mu space. So given measure group G mu, then a measure space B nu is a mu boundary if the following is true: if there is there is a G equivariant map P from the space of infinite simple paths. I will recall you to B mu such that P composed with T equals P, where T is the shift in the sample path space. So let's unravel this definition. So what is T first of all? So T is the shift. So again, omega, recall that omega was the space of what we call Wn, simple paths. So infinite sample paths. So it is a copy of infinitely many, it's a product of infinitely many copies of G, but we interpret those are the locations of the walk. And then we have this measure P, which came from pushing forward the product measure on the space of increments. So P is a natural measure on the space of sample paths. And then what is T? T is the shift. So T is a map from omega to omega and just maps Wn to Wn plus 1, the shift. And the way to interpret this is simply that you're relabeling the time along the sample path. You're not really changing the location, but just the time. So basically, in the picture, for instance, if we started the identity group, then we have W1, W2, Wn, and so forth, Wn plus 1. And so once we shift, we're just changing the time. Instead of starting from the identity, we start from W1 and so forth. So this is just a shift in the space of the sample paths. It's not the shift in the space of increments. This is completely. So recall that in fact, one interesting thing about the shift that we said at some point is that T is not measure preserving. Okay, and then what do we want? We want, basically, we want to find, so what's the idea of new boundary? The idea of new boundary encapsulates what we already have seen geometrically, that there is a point psi on some boundary that we don't know what it is, but we know that, you see, if this P composed with T equals P means that I assign to the sample path a boundary point, and if I shift the time of the sample path by 1, the boundary point is the same. And that makes sense because this is just a limit. So let me show you what is the main example, which I think will clarify everything. So an example in the geometric situation, again, we have G is a group of isometries or it's a subset of the group of isometries on some metric space. And then we know that X has boundary, some boardification. So it could be a compactification, but also did not be compact. So that's why we call it boardification. So you have X and you have some boundary. So exactly the picture that I have drawn. So we have some boundary X, and X is the space inside. And then suppose that, like we know for the disk, that almost every sample path converges. To some point in the boundary. So then we can define, we can define P, the projection, from the space of sample paths to this boundary as the limit, as n gets to infinity, of the sample path, for instance. So exactly in the usual situation. And then you get this boundary point psi, and this we can interpret as a function of the infinite path. And now, what do we want to ask? So, is this a new boundary? And is this a new boundary? And the answer is yes, because. So, okay, and then again, new would be the hidden measure. So, mu of A is the probability that the limit converges to some subset A, as we already did, and then we check that this is a new boundary. So then this with mu is a mu boundary. And what do we have to check? Well, we have to check, again, this condition that there is a map from the space of sample path to the boundary, and it's shift invariant. And so let's check that it's shift invariant. Well, again, P composed with T of some sample path or Wn is what? Is P of Wn plus 1, which is the limit and then goes to infinity of wn plus 1. Oh, you're looking at the same path, we're just changing the timeline. And so this one, of course, is, since you're taking the limit, this is clearly the same as the limit, and then goes to infinity of wn o. And so this is p of wn. Yeah. So indeed, we proved that p composed with t equals p. So this is a formal way, the notion of view boundary, to say that for every sample path, almost every sample path, we can associate. Yeah, this map is measurable, so it's almost surely defined. Yeah. Yeah, this map is almost surely defined.
Shouldn't we always also check that nu is mu stationary?
Right, so it follows, I think, from if this map is G equivariant, there are two options. Either, yeah, so I think if we do it this way, if the map is already G equivariant, then it follows from the properties of P that if you push it forward, you get it mu stationary. Vivian?
Yeah, would the 1-point compactification be a mu boundary?
It is.
Okay, and
Yeah.
there isn't anything that says different random walks in some sense have to go to different places for a mu boundary. We don't care about that.
Right, exactly. Mu boundary is this weak notion. Yeah, so it's a candidate boundary. And so, so we don't know this is the best possible boundary. But yeah, the 1-point compactification is absolutely always a mu boundary, indeed. So indeed, maybe let's write it. Indeed, that P equals 1 point with nu just the delta mass at that point is always a mu boundary.
So why did you say the mu stationary part is obvious? Is it because PT, so it follows from PT equals P, or?
Yeah, there are two options. So you can either, yeah, so here I also said G equivariant.
Okay.
So yeah, so if we combine that P composed with T is P, and I use the G equivariance, then I push forward. So then nu becomes the push forward. Yeah, I guess. Yeah, if I define it like this, I guess the nu has to be the push forward. Yeah, so I guess I should say it like that. Yeah. Yeah, a priori you could yeah, a priori you could you could start without requiring anything about the measure, and you just define nu to be the push forward. But maybe since we write it like that, we can say we can put it here, and nu is the push forward.
I see. Okay, yeah, thank you.
Yeah. So in fact, I think this calculation was one of the calculations. We will do a similar calculation soon. So yeah, you will see. Yeah. Or otherwise, yeah, you don't. Yeah. So. Yeah. Okay. Any more questions? But yeah, this is this is a good observation that we would add. Note that indeed any mu boundary is a G space, namely, yeah, if nu is P star P, we have new star new equals. In fact, okay, I guess we can give the proof here. Yeah, I was planning to do it later, but I think it fits very nicely what was said. So, in fact, what do we see? We see that mu is p star p, and then, well, p composed with t equals p, so p star t star p is also the same. So this is since p composed with t equals p. And then here there is a little exercise to do. You say that since p is G equivariant, this is the same as mu star p star p. So this requires writing down the definition of, yeah, what is this map T star and what is the action on the space of, what is the action of the group on the space of sequences. And then from there, of course, that's just by definition, that was obvious. Okay. So yeah, the only non-trivial part is this one in the middle that I invite you to try to do it yourself, because it's good to unravel the definitions. Okay, are there more questions? Okay, so now we are finally ready actually for the definition of Poisson boundary. So definition. So again, if we start with the measure group, then yeah, so basically a mu boundary, then a mu boundary. So we start with a mu boundary. B mu is the Poisson boundary or Poisson-Furstenberg boundary. So I will write Furstenberg now, and then since it's too long, I will not mention it again. But if indeed the Poisson transform which is phi from L infinity of B nu into H infinity of G mu is an isomorphism, is bijective. It's bijective. And in fact, this becomes an isometric isomorphism between these two Banach algebras if you have the appropriate norms. So on either side. So the quest is to choose to find some B nu that works. Also, we have to figure out whether this is unique. So in fact, it's unique, but it's unique in a somewhat weak sense. So we say that Poisson boundary is unique, well, as a measurable G space. So basically, it means that two such spaces where they must have a measurable function between them that carries the measure from one to the other, and also that it's equivariant with respect to the G action. So this is, it's unique in this category, but in the sense of geometry, sometimes it's slightly confusing because it could be, for instance, that you take a space that is a Poisson boundary and it will remove, say, a set of measure 0, and that it's okay. So that's this we cannot tell. So, for instance, if B nu is the Poisson boundary and B0 in B is G invariant, and of measure 0, then B0 and with the restriction of nu is also possible. But for instance, it's very clear that the fact that the boundary is trivial, on the other hand, is definitely strong invariant. So boundary is trivial. We say that the boundary is trivial if it's isomorphic to just a point. So if B equals a point with just the delta mass of that point satisfies the definition. So if the measure has only one atom, okay, this even in the category of measurable spaces, this is invariant. This is a strong thing to check. Definition, and obviously by the definition, equivalently, if the only bounded harmonic functions on G are the constants. So of course, this is the same as famous results for classical harmonic functions, so we call it the Liouville theorem. So this is sometimes called the Liouville property. That, yeah, if there's no non-trivial bounded harmonic functions, then we say that this group with a measure has the Liouville property. And then for certain groups, the Liouville property is true for all measures. For instance, for abelian groups. But yeah, otherwise there are more complicated things because this also depends on the measurement. Okay, are there any more questions? Okay, so now we can somehow get a little closer to the actual construction of this space because it's very abstract at this point. We don't even know that it exists. And I mean, in fact, the construction itself is also, unfortunately, somewhat non-constructive. So that's one of the reasons why it's indeed very nice whenever we can have a geometric construction of the Poisson boundary, like, for instance, it's the Gromov boundary or visual boundary or these kind of things. because the abstract measure theoretic definition that we're going to see is still somewhat indirect. Okay, so the construction has something to do with yeah, it is somewhat delicate in measure theory. So it has to do with the theory of measurable partitions. And so we look at the following. So again, so we look at a measured group. And then again, T from omega to omega is the shift for sample paths. And now we want to give a first identification. So the Poisson boundary is defined as a quotient. So the first thing you want to say is you say that two paths omega, omega prime in omega are equivalent if at some point after some number of shifts they coincide. So if there exists M and N such that Tn of omega equals Tn of omega prime. Okay, and so we denote this equivalence relation as equivalence relation with this T. So you see, this is the first thing that would make sense to think about, is because you see, you want to say what is the boundary behavior of the walk. And so, okay, suppose you have two paths, like a blue path and a pink path. And suppose that at some point, the two paths coincide. And they start, well, they coincide at some time, and then they start coinciding forever. Well, then obviously, whatever the boundary behavior is, it makes sense to say that the boundary behavior of both paths is the same. Well, that's an natural equivalence relation. However, it's really tricky, because if we just take the quotient of omega by this equivalence relation as a set, then we get a space which has really bad properties from the point of view of measure theory. And so that's why, in fact, it's quite tricky to give the precise definition. So the issue is that, yeah, if you look at omega and a quotient by T as a set, has bad measure theoretic properties. And so in order to get rid of that, we have to, yeah, we have to talk about organic components, and we have to talk about standard measure spaces. So, okay, so we have to introduce standard measure spaces. Okay, so first of all, when our two measure space is the same, well, that's not surprising. Whenever there's there is a measurable isomorphism between them, meaning that two measurable bijective functions. So a map F from a space X with a sigma algebra A to another space Y with a sigma algebra B is a Borel isomorphism if it is bijective, measurable, meaning that the preimage of elements in B are elements in A, and the inverse is also measurable. Okay. And the best spaces that we care about are so-called standard spaces. So a space, a measurable space, a Borel space, in a space with a sigma algebra is standard if it is isomorphic to, for instance, the unit interval with the Borel sets. So this is our favorite sigma algebra. However, it turns out that the fact that we pick 0, 1, of course, is somewhat arbitrary. So in fact, you can remark that you could pick any other Polish space. So you can take any complete separable matrix space with the Borel sigma algebra. It's Borel sigma algebra, so the sigma algebra generated by the open sets is standard. So for historical reasons, we like to start with 0, 1, but okay, we could start with any complete separable metric space. What is important is that there are these countable sets, for instance, intervals with rational endpoints that somehow filtered the whole space in the following way. Okay, so, and also what is nice about the standard spaces is that you can take subsets and products. So if M is standard and A in M is measurable, then A is also standard. So we start with a complete metric space, but then we can take any measurable subsets of it. So the original metric is no longer complete, but it doesn't matter. It's still it's still isomorphic as a measure of space to another complete metric space. So yeah, this equivalence relation is pretty weak, but still we need to say something. Okay, and moreover, the product of two standard spaces is standard. I think even the countable product, if I'm not mistaken. Okay, and then we want to put a measure on it. So far we have only sigma algebra. And we say that a measure space, not just a Borel space. So X A with the measure mu is standard. Well, if XA is standard, So we take a, so now this measure could be atomic, could have an atomic part. However, yeah, sometimes we don't want that, so we could say that the Lebesgue, yeah, the standard measure space is called the Lebesgue space if the measure of the whole space is 1, so probability measure. So basically always in our course. And it's smooth Lebesgue space if it has no atom. Okay, well, this is just a lot of definitions. But yeah, these definitions are somehow important because this is the category of spaces in which we want to work. Okay, and then we have to take a quotient, and we take a quotient by partition. So a partition of a Borel space XA is the family psi of spaces of C where, yeah, of this joint measurable sets such that the union of all of them is the space example. So nothing strange, just a usual partition. And of course, whenever you have a partition, given a partition, we have a projection map pi from x to x mod psi as a set, and then one can define Borel structure. So on the quotient by sort of pushing down the one on x in the following way, by declaring as you would imagine, like a set B is a subset of X psi is measurable if the preimage pi inverse of B in X is measurable. So again, nothing too strange. This is just a whole bunch of definitions. And so the issue, however, is that whenever and also given a probability, if P is a probability on X, we can set, you can pi star of P on X mod psi is also probability. However, the big issue here, the big warning here, is that taking this quotient can make us exit the category of measure spaces, of standard measure space. So if X a mu is standard, it is not necessarily the case that the quotient is also standard. X mod psi with this, let's say, pi star of A and pi star of mu. And that's the annoying thing, basically. Are there any questions? I'll show you an example soon. Okay, so and that's the issue, and in fact, this for this reason, we have to use what are called measurable partitions. As defined by Rothman. So again, the measurable partition is not, as the name suggests, just a partition in measurable sets. It's more, and that's the annoying part. So okay, maybe I can give you one more definition, and then we can take a break, and then we'll see an example. The definition is that a family of Borel sets separates points if for any X and Y in your space with X different from Y, there is a set B in the family such that X belongs to B, but Y does not belong to B. So the easiest example here would be if our space is the interval, unit interval, then maybe we can pick C to be the set of intervals A, B, such that A and B are rationals. So clearly, whenever you have 2 points, 2 real numbers, you can find an interval with rational endpoints, such that one number is contained in it and the other is not. Okay, so maybe it's time for a break, unless there's any questions. Yeah, so then we can, we can resume at 11:10. Hello again. Can you hear me?
Yes.
Okay, good. Okay, so we can keep going. So yeah, so finally we have all the definitions on this measurable partitions, and we would like to take this quotient, but we have to be careful. And an example indeed is the following, which is given by irrational rotations on the torus. So first of all, so we said that family of Borel sets separates points. If for every 2 points in a space, there is a Borel set in this family that such that one point is contained there and the other one is not. The canonical example is intervals in the unit interval with rational endpoints. And yes, the last definition in this context would be to say that a Borel space is countably separated. A Borel space A is countably separated. If there exists a countable family of Borel sets that separates points. Okay. So again, an example is the above one of the unit circle of the interval in unit circle. So example is indeed this one. That's why we call it our standard example. But then what is more interesting is counterexample, non-example. And the counterexample is like this. So we take x to be S1, which is arm of Z, and we take T of x to be x was alpha mod 1, where alpha is irrational. Okay. And then we take the orbits. So we take x equivalent to y if, see again, there exists m and n in z, in fact, such that t and x equals t and y. And then if you take x mod, this relation is not countably separated. And why is that? Well, suppose that there is such a set. So suppose there is a family, Bn, countable family, that separates. So now for each n, consider the partition Pn, which is the common refinement of the partition Bi and Bi complement. So basically, for each n, I can tell whether a point is in Vn or not. And so if I do this for the first n of them, I have 2 to the n sets, right? So which consists of 2 to the n sets. Now, the irrational rotation on the circle is ergodic. So, and all these are unions of orbits. So since, since all PIs are union of orbits, so they're T invariant, they are T invariant. And then, moreover, the system is ergodic. T is ergodic with respect to the Lebesgue measure. There exists always, you see, there are either each element of Pn either has measure 0 or 1. Each element Pn has either measure 0 or 1. But of course, the total mass is 1. So there has to be for each n one sequence that has measure 1. So for each n, there exists exactly one element, and what element of Pn of measure 1. So in fact, so it's equivalent to say, so setting, we can also say it another way, setting, Bi plus equals Bi, and Bi minus equals the complement, Bi complement. There is a sequence epsilon 1, epsilon n in plus or minus 1, such that precisely the measure of Bi epsilon B1 epsilon 1 intersect B2 epsilon 2 intersect Bn epsilon n and so on. So there's precisely one, and that for each n, of course, these sets are nested because the partition gets finer and finer since Pn plus 1 is refinement of Pn, means these are nested. So you can find an infinite sequence. There exists an infinite sequence epsilon n, such that indeed u of B1 epsilon 1 intersect B2 epsilon 2, Bn epsilon n equals 1 for every n. And so if you take the intersection, so mu of, you take the intersection of Bi epsilon I, this is a sequence of nested sets, intersection of nested sets of measure 1, so it has to be measure 1. Right? But on the other hand, this cannot be just one orbit. since you see the measure of every orbit is 0, because you see the Lebesgue measure is non-atomic, and every orbit for the for this rotation, for this irrational rotation, every orbit has measure 0. So you see, it cannot be that this intersection is not a single orbit. It has to be, in fact, uncountably many orbits. And so Bn does not separate points, right? Because if it separated points, if you take two elements in this intersection, then there would be some index for which x is in Bn, but y is not in the same Bn. However, the way we constructed this intersection means that every element there, either, for every element there, either it belongs to B, or either all of them belong to B1, or all of them don't belong to B1, and so forth. So the trick, again, here, of course, this can be generalized every time. Of course, remark, of course, this applies every time to any dynamical system which is ergodic and whose measure is non-atomic. Right? Because it's the same thing. Each orbit has measure 0. And so it's not enough to have countably many elements that separate points. Because by ergodicity, all the sets are indistinguishable from each other. Are there any questions? And so for this reason, we define what is called the space of ergodic components. Again, if X a mu is a Lebesgue measure space, and T from X to X measurable map. Yes, then we have to define the space of ergodic components, which then we have to enlarge the equivalence classes. We cannot just take the orbits as equivalence classes. Otherwise, the quotient is too bad. Okay, so yeah, actually, maybe let me first say another thing. Okay, So we call it, okay, so a partition psi of x is called measurable. Again, this is the theory of measurable partitions of Rocklit. If the quotient x mod psi is countably separated. And in fact, the theorem that Rocklit proved is that this is enough. So if x a mu is a Lebesgue space, xi is a measurable partition, then the quotient, indeed, x mod psi, and plus star mu is a Lebesgue space. So whenever we have a measurable partition, we can indeed do the quotient, and it's not a problem. And so this leads to the definition of measurable envelope. So we start with the partition. Then the partition psi hat is the measurable envelope of psi if psi hat is the finest, the measurable partition that is refined by xi. Right, so what is the idea? The idea is that one needs to enlarge equivalence classes in order to make the quotient Lebesgue. Okay, and in fact, the even somewhat hard theorem of Rocklit is the existence of such a thing. So if x is a partition of a Lebesgue space, then there exists measurable envelope. Of x, of psi. So in fact, the example, going back to the example of the irrational rotation, you get the following, that if if x is S1 and t is an irrational rotation, as we said before, then yeah, so basically the only way to make this measurable is to take a trivial partition. The measurable envelope of psi, which is the partition into orbits, is the trivial partition. That it's a bit disappointed, maybe, but that's what it is. So, in order to, yeah, you have to take some union of orbits, and since the since the actual map is ergodic, then the only way to do it is to put all the orbits in the same class. So clearly then the quotient is just an x mod psi hat is just a point. So yeah, so that's the only thing that can happen. And in fact, this in dynamics gives rise to what's called the space of ergodic components. So again, if we start with the Lebesgue space, T map from X to X, then the quotient of X by, not by the partition, but by the measurable envelope of this equivalence relation given by orbits is called the space of ergodic components. And denoted by X with a double bar. So in fact, this is a point if and only if the map is ergodic. Okay, so in fact, there is a universal property. which is the following. So if if f from x to some space y is a t invariant measurable functions, invariant means f composed with t is f, then f factors uniquely through x mod t. So right, so basically the diagram is like that. This x, there is x mod t, there's f, this is the projection, this is y, and then you have unique g like that. And so in general, we have, by definition, by this universal property, that L infinity of x a mu, if we take the t invariant, so the t invariant functions on x, these are canonically identified with L infinity of the quotient of x mod t with the appropriate sigma algebras a mod t and pi star. So you see, this is by it's all somewhat by construction. It's quite indirect, but it somehow works precisely because we define it so that it has this universal property. So this is in general for a dynamical system, but the Poisson boundary is a special case of this. So we can define it or construct it like this. So given again a measure group, G mu, let omega p be the space of infinite space sample paths. And t the shift. And then the Poisson boundary of G mu is indeed B Poisson mu. Poisson would be the quotient of omega p by this relation, where the quotient is in this sense by looking at this measurable envelope. So again, this is not really explicit in any way, fortunately. That's just how it is. But it shows that there is a connection between this harmonic functions and this theory of partitions and measurable partitions and this universal quotient that was introduced by Rocklin. And so basically, again, what we do is we take all infinite sample paths and we want to identify them if two of them after a time shift coincide, but this quotient would be not a Lebesgue space. And so we have to pick the finest partition, which is still much coarser than this one, that guarantees that this quotient indeed is Lebesgue. And again, this construction exists in other parts of dynamics, and this is called the theory of space of ergodic components. Okay. I don't see the screen anymore. Okay, now we see the screen anymore. Can you hear me?
Yes, yes.
Okay, perfect. Yeah, sorry, there was a short break. Okay, very good. So, are there any questions so far? Yeah, this is a lot of math and slightly disappointing in a way that the point is indeed this is not very explicit. That's the issue. Okay, so indeed that's why the big question that we really want to answer is, given a space, given again G acting on some space, and X in boundary of X modification, and then mu probability G. Yes, there are two steps. There are two steps to identify the Poisson boundary. The first one is to show that almost every sample path converges to the boundary. And the second is to show, so the first step will tell us already something quite non-trivial. This will tell us the boundary of X with mu is a mu boundary. But then we have to make sure that this is not just a mu boundary, but it is a Poisson boundary. So show that boundary of X mu is maximum. In fact, I would remark that there is a very precise sense in which the Poisson boundary is the largest of those mu boundaries. As Vivian was commenting, we can always compactify with a point, and that would always be a mu boundary. But if there are more harmonic functions, this is not good compactification. So it's similar to this theory of quotients. We cannot quotient everything to a point. I mean, we can do that, but this would be the space of ergodic components only if the actual dynamics we start from is honestly ergodic. Otherwise, this would not work. Okay, and so hence from there, yeah, hence this would be the Poisson boundary. In fact, Right. So in fact, let's recall the universal property. So much like we had before, we have a universal property. Of the Poisson boundary. And the universal property is the following. We have a diagram like that. We have omega, which projects to the Poisson boundary. So we have this projection. So this is omega p, dp mu p. And then suppose we have a t invariant map to another space lambda. Suppose there is a map like that. For any t invariant and G equivariant map F out of the space of infinite paths into mu lambda into a mu boundary. There exists a map which goes out of it, G, such that F is G composite. So any map out of the space of infinite paths that goes into a G into mu boundary at this t invariant factors through the Poisson. So this is why we say that the upshot is the Poisson boundary is the maximum of Poisson. In the sense that you do the quotient by the finest equivalence relation. So it has the most points, but still, of all the possible such quotients that respect all of the structure. And again, so here is the usual step. So whenever you're in the geometric situation, the goal is to show both things. So we have to show that, first of all, that the boundary, that the random walk does converge to the boundary, and that gives us a mu boundary. And then we want to show that this boundary that we are given is indeed the maximal one. So we cannot further split apart these points in the bound. And of course, to make this, to get a handle of it, we have to use some other tool. And in fact, this will be the entropy theory that we're going to talk about next time. So let me just finish by stating the main theorem of Furstenberg. So you see, we have the inverse Poisson transform. So we have a Poisson transform in one direction, and then we have the inverse Poisson transform. Is the following. Is a map from H infinity, G mu, to an infinity of BP nu P. But we know by definition that the space of rounded functions on a Poisson boundary is the same as the space of functions on this path space that is T invariant. This is by definition. And so we define the map like this. So given H, which is a harmonic function, you consider again Xn, which is H on the random walk. And first of all, we have to prove that this is a martingale. And so by the martingale convergence theorem, we can define lambda H on this sample path as the limit of this martingale, like we did before in similar situations. And so if the limit exists, it is shift invariant because again, it's a time limit. And so lambda of H is a function on the path space, which is T invariant, which by the universal property is also a bounded function on the Poisson boundary. So now the theorem that we still have to prove to make sure that everything works out nicely is that, again, for any measure group, and let phi be the Poisson transform from L infinity to the Poisson boundary to H infinity of G mu. And lambda is the inverse transform. Then clearly phi composed with lambda should be the identity, and the same should be true for the other one. And lambda composed with phi.
Sorry, everyone. I think I ran out of battery, unfortunately. So yeah, so we'll stop here for today. So I will present this last theorem next time. It's okay. Yeah. Okay, good. Anyways, so the next class will be in person. Anyways, so well, for the people who are in Toronto, otherwise, it's also as usual in online. Are there any questions? Okay, good. So I'll see you guys next time. Yeah, sorry about the last issue.